Here's example 2 from 16.1. Let's do another problem where we're going to use integration by parts. You might notice on this first one it asks us to integrate the natural log of 2x. So this 2x is kind of attached to that natural log. We want to find the natural log of 2x dx. And so we don't quite have an integration rule for natural logs, right? We know how to find the derivative of natural logs, but we don't quite have a natural log integration rule. And so let's try to use our integration by parts to help us kind of piece all of these things together and see if we can integrate it using our new rule for integration by parts. So if I can figure out what u is, and then I could use the rest of it for dv, then I have this piece, which then I can use my integration by parts and my other piece to figure out what the actual answer is by doing u times v minus the integral of v times du. So our first step is to pick out our u. Well, in this problem, I noticed, remember those three letters L, A, E? I noticed that we actually have a natural log in this problem. And so I'm going to call u the natural log of 2x. You can't just call it ln because it's ln of what, right? And so the 2, like I said, the 2x is attached to that natural log. So if we call u natural log of 2x, well then that means then what would be dv? Well, if the natural log of 2x is my u, well then the rest of it, remember, would be my dv. So that means that dv in this problem is just going to be dx. Or could I really say 1 dx? So now that I have u, I can find the derivative. Now that I have dv, I can find the antiderivative and figure out all four pieces. If u is the natural log of 2x, then hopefully we remember all of our derivative rules. Remember, derivatives are not going away. The derivative of any natural log is really the derivative of the inside over the original inside. So the derivative of 2x is 2 over the original inside, which is 2x. So the derivative of natural log of 2x is really 2 over 2x dx. You might notice that the 2's reduce and I end up getting a du of 1 over x dx. Now I have a u and a du. If dv is 1 dx, or 1, then what's the antiderivative of 1? What's the integral of 1? Well, that would mean then that v is really x. Because if v is x, then his derivative would be 1 or 1 dx, which is perfect, right? So now that I have all four pieces, I can plug those four pieces into my integration by parts formula. I didn't know what the derivative, or excuse me, what the antiderivative of this was, but I do know now that it looks like this, I can find its equivalent by using the u times v. In this case, u times v would be the natural log of 2x times x minus the integral of v du. Well, v is x and du is the 1 over x dx. If you notice then that my next step is going to be the x times the natural log of 2x. Be careful not to say 2x squared. You actually have to apply the natural log of 2x before you multiply it by x. So because of that rule, I don't want to get confused, and you might notice that I took this x and I put it in the front so that I don't accidentally call it the natural log of 2x squared. Maybe also putting parentheses around that 2x will help you realize that it's kind of being protected and you can't multiply it by an x yet until you apply the natural log, okay? So that first piece is just an x times the natural log of 2x. Minus, you might have noticed in this integral that I have an x on the top and x on the bottom, so x divided by x is really just a 1 dx. So now I'm just really finding the antiderivative of 1 again, or the integral of 1. Well, we know that, like before, the antiderivative of 1 is just x. So I have x times the natural log of 2x minus x, and then don't forget that plus c, that constant of integration. So that was an example where we had natural logs. Let's do another example in this video. Here's example number 2b. It asks us to integrate 2x squared plus 5 times e to the negative 3x. You might notice that I have an expression that has a variable in it times another expression that has a variable in it. I have a product rule. I can't quite use u substitution, But when I see that product rule, let's try and use our integration by parts. See if you can pause the video and pick out what you think U and dV is. Remember, when we're picking out our U, think of those three letters, L, A, E. L is for logs and natural logs, but I don't notice any natural logs in this problem. A is for any algebraic expression, and I did notice that there was an algebraic expression in this problem. I had an algebraic expression of 2x squared plus 5, so that's what I'm going to call U. If U is the 2x squared plus 5, then that means the rest of it is going to be my dV. And so my dV would be e to the negative 3x dx. Now that we have a u, find du. And now that we have a dv, let's find v. If u is 2x squared plus 5, then that means the derivative would be 4x dx. If dv is e to the negative 3x, the antiderivative of e to the kx is really e to the kx divided by k. So v would be e to the negative 3x divided by negative 3. I have all four pieces, and now I can use my integration by parts formula to plug in those four pieces. Remember, my integration by parts is u times v minus the integral of v times du. Let's plug in all of our pieces. I've got u times v. U was my 2x squared plus 5, and my v is my e to the negative 3x over 3. Minus v times du. V was the e to the negative 3x over negative 3 times du, which is the 4x dx. Now let's go ahead and simplify this a little bit. In my first expression here, I'm just going to go ahead and combine those two fractions by multiplying numerators with numerators and denominators with denominators. So in the top, I have an e to the negative 3x times a 2x squared plus 5. You can put that in any order if you want to. You can, I guess, even distribute that e to the negative 3x through to both pieces if you wanted to as well. Just be careful with how you write your terms. My denominator then is a negative 3, so that piece is as simplified as I can make it. Now let's go over here and work with the integral. I noticed that in this integral, on the numerator, I had a 4, and in my denominator, I had a negative 3. So if you were to rewrite it, it would be 4x e to the negative 3x over negative 3. And so then I noticed that this negative 4 over 3 was a coefficient. So I'm actually going to take that negative 4/3 out because it's just a number, just a coefficient, and I'm going to leave the x and the e to the negative 3x dx inside my integral. You might have noticed that these two negatives are eventually going to make a positive. And now I've got to figure out what the integral of x times e to the 3x dx is. Did you notice anything? I have an x, that's a variable, times an e to the negative 3x. That's another expression with a variable. Do you notice that this is a product rule? But we were been saying all along that there is no such thing as product rule. So what do you think that means? Yep, we got to do integration by parts again, 2 times in the same problem. Because I have an integral that I have two things being multiplied, two expressions with variables, we're going to go ahead and integrate it by using integration by parts. So what do you think u and dv would be in this integral? I didn't notice any natural logs or logs, but I did notice that I had an algebraic expression of x. So I'm going to call u x. That means du is 1, or 1 dx. That means I'm going to call the rest of it dv. That's the e to the negative 3x dx. The antiderivative then is e to the negative 3x over negative 3. Okay, so that means this integral here is going to turn into an integration by parts after I plug in all the different pieces. I still have the first piece, that comes from here, and then I still have this plus 4/3 that's out in front. And this 4/3 has to be distributed to everything that the integral equals. So when I use my integration by parts, I have to make sure I distribute the 4/3 through to all my pieces in the end. Remember, my integration by parts formula was u times v, so I plugged in those two pieces, minus the integral of, what was it, v times du. I'm going to make sure that I distribute the 4/3 through. When I do that and I distribute the 4/3 through here, I have a 4 on the top and a -9 on the bottom. That made me a -4/9. I have an x and an e to the -3x in the top. I'm also going to distribute the 4/3 through here. On the top I have a 4, and on the bottom I have a -9, but then another negative. Woo! You might want to rewind that and look at that. That's a 4/3 times, really, a positive 1/3. Did you get it? 4/3, and then those two negatives made a positive, and then I had another 3 in the denominator, so 4/3 times a 1/3. Whew, okay. But then inside my integral, I still had this piece that was the e to the -3x dx. You might need to run through that a few more times. Try to ignore all my scribble scrabbles here and figure out how that 4/3 gets distributed and how I can simplify it a little bit so that I can finish my integration in that last piece. Okay, so I have this first piece I haven't touched. I have this second piece now that's as simplified as it can be. This turns into a 4/9, and then I have the integral that I still need to do of e to the -3x. So the antiderivative, or the integral of e to the kx, is just e to the kx divided by k. So that's where I got this term of e to the -3x divided by -3. Don't forget to multiply it, though, by that 4/9 that's in front. And so my final simplified answer for the integral of this problem would be this beautiful, or ugly, I'm not sure what you would say about this expression. Don't forget your constant of integration in the back. Be careful with all your positive and negative signs. Be careful with distributing that 4/3 through to everything. That was kind of an ugly problem, or a good problem, depending on what you think of that, but 2 different integration by parts in one problem. So you might see that throughout, depending on what that last integral ends up being. If it ends up being another product rule, well, then that means you're going to have to do integration by parts twice. Practice that one. That was a good one to test you on your integration by parts, and we'll do one more example in the next video.